Welcome to this presentation on the Kelly criterion. My name is Doyle and I'm a student in the University of Limerick. So firstly, what is the Kelly criterion? It's a formula that gives the optimal fraction of your bankroll that you should wager in each bet in order to maximise the growth rate of capital whilst avoiding the risk of ruin. It's a fixed fraction, so you constantly bet the same fraction of your current wealth. So this means that the amount you'll be betting each time will be dependent on your current bankroll. The Kelly criterion can only be used when the gambler has an edge, so this is when the person knows that the odds are slightly better than the odds being offered. Someone will have an edge if they know that the coin is biased, for example, so the formula is F star equals 2p minus 1. So Kelly's criterion is typically used in blackjack or sports betting. It can also be used in the stock market, where the main objective is to invest so as to maximise the expected growth rate of capital. So firstly, I wanted to see how the expected log wealth and the log of the expected wealth compared. Kelly's criterion is the expected log wealth, which is represented by the first formula here. By differentiating this, we deduce that the expected log wealth is optimised when f equals 2p minus 1, and this is Kelly's optimal f star. Now, to see where the log of the expected wealth is maximised, we will focus on the second formula here on the top right of the slide. When we differentiate this, we deduce that the log of the expected wealth is optimised at f equals 1. So what this suggests is that the larger the fraction of your bankroll that you wager, you will maximise your expected wealth. But this is different to Kelly's optimal f. If a gambler wagers a fraction that is too large, they risk overbetting. This is why Kelly's formula optimises the expected log wealth rather than the log of the expected wealth, and thus maximises the player's bankroll. Depending on their level of risk aversion, individuals can use different fractions of Kelly's optimal f star. For example, half Kelly, which is 0.5f, or double Kelly, which is 2f. Here we can see how Kelly's f star compares for different fractions of f. I compare the standard deviation and expected wealth of 100 different values of f from 0 to 1 in a step of 0.01. After having already discovered that the expected wealth increases with f, which we discussed in the last slide, I was not surprised to see the results of this plot. As anticipated, both the standard deviation and expected wealth increased when f was increased. This makes sense, since an individual who is increasing the amount that they bet will certainly increase their bankroll and consequently will increase their variability. This corroborates our claim that when a more aggressive betting strategy is used, the player can expect to have a larger bankroll, but it's also much riskier. It is evident that if one was to wager their entire bankroll, or even close to it, they risk losing a significant sum of money. Similarly, the variability dramatically increases to exceedingly high levels. Following this, I wanted to see the relationship between the standard deviation and the expected wealth for different values of f, and hopefully get a clear understanding visually why Kelly's criterion optimises the player's bankroll. To make it a bit more informative, I also changed the fraction being wagered, and presented my findings on a graph. As we can see, when the probability of heads appearing is only 55%, it means that the edge is quite small. This allows us to witness Kelly's conservative nature. The expected value is very low, which we can see from the red circle in the bottom left of the graph, but we can also see that the standard deviation is very low. When the edges increase slightly up to 60% and 65%, we can see that the expected value and standard deviation also increase slightly, but are still very low compared to when larger values of f are used. As well as that, the varying probabilities allow us to make a comparison for different edges. We see that when the probability of success is higher, there is less variability for different expected values. This is because the individual success is more certain, thus there is less variance. This graph illustrates how Kelly's criterion optimises bankroll. Whilst the expected value is significantly lower, the variance is also much lower. This is why it is an ideal method for risk-averse individuals. This leads me to discussing risk aversion and the log utility function. Kelly's criterion is aimed at risk-averse individuals. It's a log utility function, which is concave. Risk aversion requires that the utility function is concave, and so therefore it optimises the player's bankroll for risk-averse individuals. It prevents the player from losing a significant amount of money. Generally, people tend to be risk-averse. They would rather minimise winnings if it also means that they will minimise losses. This is the basis of Kelly's criterion. Optimal Kelly, which is the f star that you get from the formula, avoids the risk of ruin. Since you're always only betting a fraction of your wealth each time, you can never lose all of your money. This is why it is an ideal betting strategy for risk-averse individuals. However, whilst Kelly's criterion is a fantastic betting strategy for risk-averse individuals, it also has its shortcomings. The fact that it's only aimed at risk-averse gamblers is a massive pitfall in the Kelly criterion. Whilst generally people do tend to be risk-averse, this is not always the case. Therefore, Kelly's criterion might not be the best strategy for risk-seeking or even risk-neutral individuals. It's also worth mentioning that it is quite difficult to have an edge. Since Kelly's criterion depends on having an edge that the player can be confident in, it can only be used in certain circumstances. As well as that, it can be difficult to determine the edge in many scenarios, such as horse racing or sports teams, since personal preference or a poor performance may play a part in deciding the edge. Finally, there is also significant volatility in the short term, which is why the benefits of Kelly's criterion are usually seen in the long run. However, an individual might not intend to gamble in the long run, and thus it may not be the best strategy for them. That's why it's important to account for these disadvantages when deciding if the Kelly criterion is the right strategy for your individual preferences. So after having only analysed Kelly's criterion for independent, identically distributed random variables, I turn my focus to correlated coins. This is when the outcome of the current coin toss depends on the outcome of the previous coin toss. Again, F* is the optimal fraction of your bankroll that should be wagered in each bet. Here we can see a slightly modified formula, taking into account the outcome of the previous coin, where P0 is a probability of heads on the first flip, and P infinity is the probability of heads in the long run. Omega is the correlation. Using Monte Carlo simulations, I obtained the expected wealth and standard deviation for a 1-bet game up to a 10-bet game. So for the first top two plots, omega 0 equals 0.8 and omega 1 equals 0.1. This meant that there was a very high probability that heads would appear, and there was a slightly strong positive correlation between the current coin toss and the previous coin toss. For the bottom two plots, omega 0 equals 0.65 and omega 1 equals 0.2. So the probability of heads appearing was high, and again there was a positive correlation between the current coin toss and the previous coin toss. We can see that as the number of plays increased, the expected wealth and standard deviation also increased. Interestingly, we can see that there is slightly more variability when the probability of heads appearing is 65%, since this means that there is less certainty. Following this, I carried out an analysis of the Kelly criterion in the stock market. In the case of the stock market, a slightly modified formula is used, since we have to take into consideration the values of the upticks and downticks. So I used two different cases here, which were both approximations. The first case compared the stock market to a biased coin, where I just took an uptick to be +1 and a downtick to be -1. This is the red line, as seen in the plot. Following this, I used the formula seen here. The results of this are seen as the black line. When using this updated formula, I obtained a larger value of F than I did when likening the stock market to a biased coin. Even though I used half Kelly, I was still wagering a larger fraction. This is evident in the plot. As the stocks were rising, the larger fraction meant larger earnings. However, as soon as there was a large drop, as seen in May, the larger fraction causes a much larger drop in the player's bankroll. It was then difficult to pick back up to the same level as the original formula. This perfectly elucidates the volatility that is seen in the stock market, and highlights the implications that this volatility can have in the short term. However, as we can see by December, the stock starts to rise again. If it continues to rise, the updated formula will soar higher than the original formula again, since a larger fraction is being wagered. This illuminates the desire for Kelly's formula to be used in the long term, and also the importance of using fractional Kelly in the stock market. I thoroughly enjoyed researching the Kelly criterion. It was a very rewarding experience that allowed me to expand my knowledge in mathematics, statistics, and the world of gambling. I have learned that once a player has an edge, it is always possible to use the Kelly criterion to optimise your bankroll, even if that means using the fractional Kelly if your edge is not certain. Aaron Brown stated in The Secret History of Wall Street that the Kelly criterion allows the gambler to get rich exponentially slowly, and I think that statement epitomises the Kelly criterion. Thank you for your time, and I'd be happy to answer any questions you may have via email.